talk about some easy stuff, so you can relax and enjoy. So my talk has 4 parts. So part 1, I'm going to give a very brief introduction about what is called optimal transport. And then we move to application in geometry, show you how to use optimal transport to prove some inequality in geometry. Then we move to more applications. One of them is in image recognition, and the other one is in cosmology. We're trying to use optimal transport to study the Big Bang theory, to understand how the universe is evolving. Last part, if we have time, I would like to introduce some recent results on free boundary problem in optimal transport. All right, now let's see what is optimal transport. So imagine we have an initial domain, omega, and we have a target, omega star. Over omega, we have some kind of distribution. I'm assuming it's given by probability measure rho. And the omega star, we have a different kind of distribution. It's given by probability measure rho star. By transport, I mean we need to find a mapping T from omega to omega star. But that T has to be somehow reasonable, which is in mathematics called measure preserving. So measure preserving, that means it preserves the local measure. So imagine you have a subset E in omega star. The pre-image will be T inverse E, and the measure over these 2 small domains should be balanced. If the mapping T satisfies this condition, we say it's measure preserving. Okay? Now, what does optimal mean? Optimal means we have a cost function, Cxy. So Cxy, the meaning of Cxy is if you transport a location X to location Y, how much it costs you. It could be how much money, how much energy, how much time, depend on your applications. Okay? Now, once we have the cost function, if you use a mapping T to finish your job, how much in total it costs you is given by this functional. Okay? So optimal transport is trying to minimize such a functional to find the minimizer. The problem heavily depend on the cost function. So different kind of cost function give you different kind of solution. So that's easy to understand. Let me give you a discrete case example. Because the first cost function given by Monch in 1781 is x minus y, the Euclidean distance. But however, it's pretty bad. I'll show you why it's bad. So imagine you have 3 points in R1. Okay, so everything in R1, and you have 3 holes. You're trying to move the 3 points into the 3 holes. Okay, if the cost function is x minus y with a power p, this p is strictly bigger than 1, then it's pretty easy to calculate. The optimal way is left one goes to left, middle one goes to middle, right one goes to right. That's an optimal solution. If the cost function is p bigger than 0, less than 1, you can show the optimal one should be left one goes to the right, and the middle one middle, and the right one goes to left. You have to flip everything. Okay? The reason why is this guy is convex, strictly convex. This guy is strictly concave. But x minus y with power 1 is pretty bad. In that case, if the cost function is x minus y, it doesn't matter how you map in omega to omega star. As far as 1 to 1, the cost is always the same. So that means no uniqueness. In mathematics, if you do not have uniqueness, sometimes it's a disaster. It's pretty bad. Okay, so that's why the problem, it takes more than 200 years to get a final solution. Of course, we can consider different kind of cost function. If I change the cost function to log, we have application in reflector problem. I'll show you in 1 minute. And similarly, if I consider the log inner product xy, it has application in geometry, which is called Alexandrov problem. And for PDE, from PDE perspective, our favorite one is quadratic. It's a cost function given by x minus y squared. Okay, I tell you what's the reason. One of the reasons is the PDE is the standard Moudon pair. And moreover, if the cost function given by quadratic, this quantity actually gives you a distance between the probability measure rho and the rho star, which is called Wasserstein distance. Of course, you can change the power 2 to power a different power. It gives you the p Wasserstein distance between the 2 probability measures. Okay? Now let me show you what do I mean by reflector problem. So imagine the light is shooting out from the origin along different direction. So each direction you have different kind of density given by rho, and here you have a reflector. So when the light's touching the reflector, it will be changing direction. It's reflected downwards and eventually illuminate another target. Okay? So the problem is, given initial data here and given the target information here, how can you design such a reflector so that the whole system is satisfied? Okay? So the problem is actually we can formulate this problem into optimal transport, and the cost function exactly the log cost function. Okay? It has many real-world applications, for example, the satellite design and also the microscope. Okay? So, I mean, as far as we can consider reflector, we can also consider so-called refractor, right? So imagine the light is passing through one media into a different media, and you have a hypersurface here. So when it crosses a hypersurface, it's changing direction, okay? So similarly, given all the initial information, the target information, how can you design such a hypersurface? This has an everyday application when we drive in the car. The headlight is actually not flat, it has a curve, okay? So how to design that curve such that the light being reflected strictly way to the direction, whatever you want, okay? So that's lots of the design problem. So what's the advantage we formulate this kind of problem into optimal transport? One of the reasons is if we look at the satellite design, the satellite is actually many small pieces, they pinch together, put together. It's not smooth. It's a lot of the small piece, small mirror put together. So imagine the hypersurface, okay, you have n small mirror here, you have n small mirror there, so totally you have n square small mirrors. So if you use a traditional method to calculate the curvature of each mirror, the what's that called? Complexity of computation will be big O square. But by formulate into optimal transport, it becomes big O n. So that's a big improvement, okay? So that's why people very curious how to change the formulation into optimal transport, okay? So similarly, we can talk about numerical approximation and design different kind of algorithm, okay? Now let me tell you the real reason in PDE we prefer the quadratic cost function. If the cost function given by quadratic, the Brunn is a French mathematician. Brunn told us this optimal mapping not only exists unique and is given by a gradient of a potential function. That potential function is convex, and it satisfies the standard Monge pair. Okay, so that's a PDE comes in. And of course, we have the natural boundary condition. That's a du omega, because du is a mapping, right? Du mapping everything from omega to omega star, okay? And this boundary problem not only coming from optimal transport, it also has a geometric application in minimal surface. So for example, in R2, imagine you have two domains, omega and omega star, with same area. We're trying to find a diffeomorphism, which is area preserving from omega to omega star. If no more restriction, such a diffeomorphism has infinitely many by using a complex theory, Riemannian mapping theory, right? You have two domains, you can always map into a disk and then go forward, right? And here, I assume one more condition. If you consider a graph of this diffeomorphism, that will be a two-dimensional submanifold embedded into R4, right? I assuming that submanifold is minimal. So in that case, we can prove the diffeomorphism is given by a gradient of convex function. And that convex function exactly satisfies the Monge pair because it's area preserving. So right-hand side part is equal to 1. And the boundary condition du omega equals omega star. So that's similar problem, but different kind of applications, okay? In PDE, we always trying to understand what's the regularity of the solution, especially what's the global regularity. So before I talk about global one, let's look at some interior result. So in 1990s, Caffarelli told us if the U is a strictly convex solution to the Monge pair, as far as the right-hand side part is bounded from below and above positive, okay? And Caffarelli can prove the solution is C1 alpha for some alpha from 0 to 1. If we go further, if the right-hand side part is continuous, all VMO, and we know the solution will be W2P for all P from 1 to infinity, okay? And one step further, if the right-hand side part is C alpha, we know the solution is C2 alpha. That's a Schauder estimate. Once we have the Schauder in second order PDE, we can always go further. So that means if right-hand side part is smooth, solution will be smooth. That's the end of story, okay? So that's for interior. Now, what's for global regularity? Global regularity, that means how smooth the solution up to the boundary, okay? So Caffarelli in 1992, he told us, as far as the domain omega star bounded and convex, and right-hand side part satisfy doubling. So do not worry about doubling. You just assume it's bounded from below and above, okay? And Caffarelli proved the solution will be C1 alpha globally up to the boundary, okay? Now the question is, how about higher order? Because C1 alpha is not enough for our application. So what kind of application? Now let's look at the very easy application here for isoperimetric inequality. So this is one of the oldest inequality in geometry, I reckon, maybe 1,000 years ago, right? And nowadays we have many different kind of proof using symmetrization and the harmonic analysis and the probability theory, geometric flow. I mean, many different kind of proofs. By using optimal transport, I show you a very quick proof, okay? So what does isoperimetric inequality means? In this talk, we focus on R2 because the picture is easy to show here. So assuming we have an arbitrary domain D, we use A to denote the area, and we use L to denote the length of the boundary. So we always have L squared is bigger or equal than 4 pi A. If we have the equation, it has to be a round disk, okay? So that's called isoperimetric inequality. Now let me show you how to prove this by using optimal transport. Step 1, I'm going to choose a convex envelope of the D. So that means it's a convex set contain the given domain D. The smallest convex set, okay? So that means it's called convex envelope, okay? So we can claim in order to prove isoperimetric inequality for D, it will be sufficient to prove that for omega. It's pretty easy from the picture, right? Because it's monotone. The length of the omega becomes smaller, but area becomes bigger. So you look at the inequality, one goes to left, one goes to right, okay? So that means we look at isoperimetric inequality for omega. And step 2, I'm going to choose a disk that has exactly same area of the omega. So therefore, the radius is decided by area omega over pi square root, okay? Now I'm going to use optimal transport. Of course, I'm using my favorite one, cos function equals quadratic, okay? So cos function is this one. So Brunn told us there exists a mapping T, which is given by du, mapping everything from omega to omega star. And moreover, because of density, I'm using a Lebesgue measure, okay? So the density will be constant 1. So therefore, we have the Monge pair determinant d2u equals 1. Sorry. Monge pair, right? So this d2u is a matrix, n by n matrix, right? Because we have the students here. So d2u is n by n matrix, and you calculate what's the determinant of that matrix. Okay, it gives you a quantity. This equation is called Monge pair. Okay, now we have the Monge pair, and we have the boundary condition du omega equals omega star. Now I'm assuming the solution is smooth up to the boundary. It's smooth globally. Now we can calculate the area of the omega is exactly equal to constant 1 integral over omega. So I change the constant 1 to determinant. Once we have the determinant square, because it's constant 1, it doesn't matter you use the square or not. Okay, I can use the A mean, G mean. So this one is always less or equal than Laplacian, half of the Laplacian. So if you look at the eigenvalue, here is a product of two eigenvalue, square root. It's a geometric mean. And here, Laplacian is the sum of two eigenvalue and divided by 2. That's an algorithm mean, right? So we have this inequality. Once I change the Monge pair to Laplacian, I can use what's that called? Divergence theory, right? I can reduce the integration up to the boundary. Then you use a Cauchy-Schwarz inequality. So this is always less than the length of this vector du. But what du means is mapping everything from omega to omega star, so therefore du is always less than the radius. Okay? So the du, the length of the du is always less than the radius r. And radius r is explicitly given by the formula here. So you put everything, organize everything from right to left, it gives you isoperimetric inequality. Okay? So that's pretty straightforward. But everything is under this red color assumption. I assuming the solution is smooth globally. Question is smooth or not globally? So it's given by, in dimension 2, it's given by Delanoy, and then higher dimension by Urbas from Canberra, from NU. And what they prove is they assuming a two-domain uniformly convex, and then as far as the right-hand side part is smooth, the solution will be smooth globally. Okay? And 1996, Carfelli gave a very sharp, a little bit sharper than the result here. Okay? He removed the regularity of the domain, and also he reduced the regularity on the right-hand side part of the PDE. So Carfelli actually proved, as far as the domain is uniformly convex, right-hand side part of the PDE is C alpha, then solution will be C2 alpha globally. Okay, so normally the story end up with C2 alpha because for elliptic PDE, second order elliptic PDE, once you have C2 alpha, you have C infinity. Okay, okay. So a summary. What does the uniformly convex mean? That means the curvature has a positive lower bound. Okay, if the domain is uniformly convex, everything is perfect. Okay, they already prove. If the domain not convex, we do have the counterexample to say the C1 is not true. Okay, so that's the end of the game. Now the question is, how about the critical case? So the curvature is non-negative, so that means the domain is convex but not uniformly convex. And why do we care? Look at convex envelope. This convex envelope is convex but not uniformly convex because the curvature here it becomes 0, right? So that means it's one of the motivation we do care about a critical case. So that's the joint work with Shibing Chen and Xujia Wang. We relax the uniformly convex condition. As far as the two domain is convex, that's good enough. We can prove if the right-hand side part is C alpha, solution will be C2 alpha globally. Once we have C2 alpha, we can go to C infinity by standard regularity theory. So our theory can be applied to convex envelope perfectly. Okay, we do not need the curvature has a positive lower bound. All right. Actually, by using optimal transport, we not only can prove isoperimetric inequality, we can prove lots of the geometric inequalities. So one of the another example is a Brunn-Minkowski problem inequality. So what does that mean? That means assuming we have two domain omega and omega star, we can define the addition omega plus omega star. So that means for any x in omega, for any y in omega star, we just put them together. Okay, so that's a sum. So this inequality, Brunn-Minkowski inequality, tells us the nth root of the volume of the sum is always bigger or equal than nth root of the volume omega plus nth root of the volume omega star. Okay, so that means the nth root of the volume is a concave function. Okay, we can use optimal transport to prove this inequality. Half page is pretty quick. Okay, so assuming we have initial domain omega, target domain omega star, I normalize the density. Assuming density is here, so therefore the total mass is constant 1. Okay, now I use my optimal transport. Cost function is quadratic. I didn't write it down. And we have the Monge pair determined D2U is equal to the rho over rho star. It's given by a constant. Now let's calculate what's the volume of the sum. The volume of the sum is exactly constant 1. So here is a constant 1. The constant 1 integration over this domain. Okay. So I change it to identity plus du omega y, because identity applied to omega is omega. Du applied to omega is omega star, right? It's constant 1. Once we have this integration, I can use a so-called change a variable, right? So I change a variable, you have the mapping, the Jacobian matrix of this mapping. Yeah, that's exactly the determinant. So determinant plus identity plus d2u, the integration over omega, and then I use a concavity of the Monge pair operator. So I end up here, but this is a constant. So put constant in, and you play a little bit. You have the Brunn-Minkowski inequality. Okay, so that's half page. It's pretty easy. In fact, these two inequalities are related to each other, right? If you linearize the Brunn-Minkowski inequality, you got isoperimetric inequality. What do I mean by linearize? So the Brunn-Minkowski inequality tells you omega plus omega star in this root is always a concave function. And now I choose a special omega star. That's B epsilon. Okay? If I choose omega star to be B epsilon, I have this inequality. Now for students, you look at the left-hand side part, it's very familiar. That's exactly the definition of derivatives if I take the epsilon goes to 0, right? So that's called linearize. Now, okay, so this is how to, this is actually tells you how to take the limit. Now, if I let the left-hand side part epsilon go to 0, I use a chain rule. If I use a chain rule, it gives you exactly the nth root, your derivative, you put 1 over n in front, and index become 1 over n minus 1. And the other factor is exactly give you the boundary of the domain. Okay? So this, you play a little bit, that's exactly the isoperimetric inequality. Right? And question? This part is very easy to understand. Okay? Imagine you have a screen, it's omega. What does omega plus B epsilon? That means you put a small ball, B epsilon, everywhere, right? So you take the volume minus omega, that's exactly the area of the, what's that called? The boundary, right? You put a little bit boundary over here. Then you divide epsilon, that's the width. So therefore it gives you the length of the boundary, right? So everything is very fundamental. All right, now let's look at some nice picture here. So recently, people told us if you want to study the medical image processing, it's related to the optimal transport from a square to square. If in higher dimension, it's from a cubic to cubic, from a cube to cube. Okay, this is very important because for the brain surface analysis, people trying to understand what happens here. But we know the image of the brain is zigzag. There's lots of the zigzag, right? It's not so clear. So we're trying to stretch it out. Okay. You have the orange here. You're trying to stretch it, make it flat. Okay. There's two methods. One is using conformal mapping. So conformal mapping to here, it doesn't change the angle. So therefore, it doesn't change the shape, the geometric shape. But however, it will change area. The other one is by using optimal transport. Okay. It may look different, but however, the area doesn't change. So it's pretty helpful for the doctor because if there's some tumor, we care about the volume of the tumor, right? So you always want the volume is preserved, not the angle is preserved. So that's the advantage of using optimal transport by, rather than using the conformal mapping, okay? However, the previous work does not apply to the square. The square is convex, everything is fine. But however, you have the bad points. That's the angle. For the angle points, you do not have the regularity. So that is pretty bad. In dimension 2, Jerry told us as far as the density is C1 alpha, then the optimal mapping T will be C2 alpha. And he also gave us a counterexample, tells us that C2 alpha is the best we can expect it, because C3 never true. Okay, so C2 alpha is the best one we can prove. But however, his result is only applied in dimension 2, because in dimension 2, we have a special technique, which is called partial Leondar transform. So partial Leondar transform, recently I realized it's pretty powerful because it can change a fully nonlinear PDE into a quasi-linear PDE. And if the right-hand side part is equal to constant, then it directly goes to Laplacian. So if you have a PDE is fully nonlinear, normally it's pretty hard. But by using partial Leondar transform, you can change everything from fully nonlinear directly to linear case. So life will become much easier. But however, it's only applied in dimension 2. In higher dimensions, such a technique does not apply. Okay. Somehow it's also related to the convex analysis. Because in R2, everything can be using complex function to represent. But higher dimension may not be true. Okay. Now the question is, in higher dimension is in our joint work, we prove such a global regularity for higher dimension. So as far as the right-hand side part is C alpha, C1 alpha, we can prove the optimal mapping T will be C2 alpha. And as I mentioned, this is the best result we can expect it, okay? So our method is a little bit different. It's very naive, okay? So the bad guy is a corner. And the domain is very special. It's a square or it's a cubic. So in order to handle this bad guy, we just put them, evenly, such that the sharp point becomes interior point. Once this bad guy becomes interior, we can use interior regularity to handle the boundary, okay? It sounds very naive because, everyone knows like the block, right? You build in the brick, you put the corner, become interior. But you lose something. What you lose is exactly the smoothness, regularity of the function. Imagine even you have a smooth function, okay? Even you have a smooth function. It's very, very smooth, okay? You do an even reflection. Even reflection, that means this is symmetric, right? At this point, you lose regularity. Even here is C infinity, but here is only ellipses, right? So that's pretty bad. Something you gain is a geometric obstacle, right? You conquer the sharp point, but something you lose is regularity. But however, if you look this more carefully, you can realize you did not lose too much. You only lose the regularity along one direction. Along all the other direction, this is x1, okay, this is x prime. You only lose regularity along x1 direction when you do the even reflection. Along all other directions, it's still smooth, okay? So it gives us some kind of idea to use a partial regularity of the PDE. So normally, if you consider degenerate PDE, if one direction goes wrong, life is not that bad. We can use a good direction to compensate the bad direction. If two directions goes wrong, that's the real trouble. Okay, so normally it happens for elliptic PDE. Okay, I removed all details. Okay, all right, now let's look at the application in cosmology, the Big Bang theory. So Big Bang theory tells us the universe is starting from the singularity, and somehow we don't know what happens. There is a Big Bang, so everything is coming to evolving. Okay, so first we have a little bit star, then we have the galaxy. And this is a picture of today, okay? So the question we're trying to understand is, imagine 1 billion years ago, we have a picture here. And today, we have the picture here. How does things evolving? So why 1 million years ago the picture become today? How each galaxy or each star is moving. So that's a question we're trying to understand. Previously, people using a system to model this kind of system. So, for example, the rho is a density function, and the v is a velocity. So density means, that's a picture from nature. The density means if it's very bright, the density will be high. If it's dark, black, the density is low, okay? So we use that one to represent the picture of the universe. And we have the velocity field v, then we have the transport equation. And second one tells you the acceleration. And the third one tells you where does the force come. It's actually coming from, what's that called? Attract each other. What's the word? Oh, yes, gravity. Yeah, exactly. So that's a gravity. So you put these three equations together, it gives you a system. But these three equations is tangled with each other. So each one looks very easy. We learned from year 1 or year 2 PDE. But if they tangle with each other, it becomes pretty hard, okay? And such a system looks very similar to me, give me a feeling of the fluid mechanics. But I have no idea how they are related to each other, but it just looks very similar. Okay, maybe there's some secret behind. Okay, so therefore, it's pretty hard to handle. Even nowadays, how to define the weak solution is not so clear to me. Okay, now we change the idea. Can we formulate everything into optimal transport? Because optimal transport is what we can do, right? So in 2006, Gregor Loper, he actually tells us the previous function, the previous equation has a variational structure. So the first part is the kinetic energy, Second part is the potential. It's coming from gravity. It's coming from gravity. So you have two energy. And if you minimize this functional, it goes to the equation. Oh, sorry. It goes to equation here. Okay. And in our joint work, we're trying to change the gravity to a more general potential function. And as far as we give some kind of condition for this function curved f, we can formulate everything into optimal transport. So initial domain, target domain, and how you transport everything from 1 million years ago to today's picture. Okay? And by using optimal transport, we can prove as far as the density function is LP, the velocity field will be C alpha. As far as the density is smooth, then the velocity will be smooth. So everything is smoothly evolving. So far we are safe. Okay, there is no bad thing will happen. Okay? Let me see, time. Okay, we still have time. Now in the second part of my talk, I'm trying to introduce the optimal partial transport. So what does optimal partial transport means? Optimal transport is moving everything from omega to omega star. But partial transport, that means I'm not going to transport everything. I only care about half of them or a quarter of them. Okay. Then you have to decide which part is going to be transported and which part is not. So in real life, it's somehow the supply is strictly bigger than your demand. Okay, you do not need so much stuff. You only need part of it. Then you have to decide which part is going to omega star and which part is stay. So you have to divide into two parts, and the hypersurface is called free boundary. And this problem also has application in natural language AI. For example, the text summary. Imagine you have a very long article, 10,000 words or something like that, but you're pretty busy. You want only read the summary, right? So the AI need an algorithm to tell you which word is more important. So which word you pick up and which word you can ignore. So you pick up and ignore, it gives you a free boundary, okay? And also we have more application in financial mathematics that I'm not very familiar. I just put a name here. So from PDE perspective, we're trying to understand what's the regularity of this hypersurface. What's the regularity of the free boundary, okay? To study the regularity of the free boundary, the key observation is a so-called interior ball condition. So what does interior ball means? Imagine you have a point on the free boundary. Its image is being transported into the Tx. You're using this as the center, using the length as the radius, you draw a ball. That ball, the sphere, you draw a sphere. That sphere is always on one side of the free boundary. That's the lemma here. I can prove by using the picture very quickly, but it's not precise. Okay, just give you the idea. Imagine if it's not on one side of the free boundary, it will cross the free boundary transversally. Okay, if it crosses the free boundary transversally, you can question, why do I move the black point to here? Why don't we move the red point to here? It saves a lot of distance, right? So therefore, it will contradict to the optimality. Okay, it's just an idea how to prove this interior ball. This.
Do you have a cost function for the boundary, or do you like how to control?
Yeah, good question. Cost function is a distance function square.
Okay. So
yeah. Yes. Yeah, very good. If you change the cost function, it may not be a ball, it be another kind of support function. Yeah, very good. Yeah, because from this part, I always focus on my favorite cost function, the quadratic cost function. Okay, this observation actually give us lots of the information about the free boundary, because every point you have a support sphere. Every point you have a support sphere. So therefore, the free boundary must be semi-concave, right? At least you have a little bit of regularity. It's a semi-concave hypersurface, okay? And can we move a little bit further? It's given by 2010, Caffelli and Robert McCann from Toronto. They prove as far as the two domain omega star separate from each other, and right-hand side part is bounded, then they can prove the free boundary C1 alpha. So that's a little bit further than semi-concave, because semi-concave, usually you only know it's ellipses. That's the best one you can know, but now they can improve it a little bit to C1 alpha. And Figali, Alessio Figali and his PhD, Indri, they actually tells us I do not need to assume two domains separate. They can have some kind of overlap. But then, as far as the free boundary do not touch the intersection, they prove the free boundary will be C1 and C1 alpha. Okay? But if it touch the intersection, there's no further information about that one. Okay? Now the question is, how about higher order regularity? Because as I mentioned, our research area is a second order elliptic PDE, so we always expect we have C2 alpha, because C2 alpha is the ideal one. Okay, once you have that one, you can go to C infinity. But C1 alpha is a little bit, lower. So the question is, how can we prove the higher order regularity? So this was finally solved last year in a joint work with Shibing Chen and Xu Jiawang. We can prove, as far as the domain omega is bounded, I do not need any convexity. But target, we assume in C2 and uniformly convex, and they separate from each other. Then we can prove, as far as the density function is C alpha, the free boundary will be C2 alpha. Once you arrive at C2 alpha, the story will be end. Okay, you go infinity. What's the trouble? What's the difficult in studying this problem? It's exactly the free boundary. In general, there's no convexity. If the free boundary is convex, then essentially you're moving something from convex to convex. It's well understood, okay? But in general, the free boundary, it could be zigzag. There's no control of convexity. So that gives you a lot of trouble, okay? And our idea to handle this trouble is by using obliqueness estimate. So what does obliqueness mean? What does obliqueness means? You look at a point, it's mapping to another point. Over here, you have a normal direction. And over here, you have another normal direction. These two normal directions give you an angle. Obliqueness, that means, strictly obliqueness, that means we have to control this angle is strictly less than pi over 2, okay? If you think about this a little bit further, it's mapping by a gradient of convex function. So therefore, the angle is always less or equal than pi over 2. But what we need to prove is strictly less than pi over 2. Okay? So it's very similar as the Hoffe-Lemmer for Dirichlet boundary condition. So Hoffe-Lemmer, the Neil told me is one of the most important results for Dirichlet boundary condition. So that means in general, you have less or equal than. But here, we have to, somehow you have to control, it's strictly less than, okay? So once we have obliqueness estimate, we can prove the regularity on the boundary. Okay, so that's a key part. Question is, okay, here the regularity, that means is smooth inside. Now the question is, how about global regularity? So global regularity, that means what's the regularity at the corner, okay? So in order to study the global regularity, we have to divide into two cases. One case, because we have two boundaries. One is a free boundary, the red color. The other one is fixed boundary, the black color. They will cross each other. How do they cross each other? They could cross each other transversely or very smoothly, tangentially. Okay, you have to divide case by case. Okay, so this is a joint work with a student. So we can prove the free boundary is almost C11, and this is sharp. Because we do have a counterexample to show the C11 is never ever true. Okay, so we can prove it's C1 1 minus epsilon for any epsilon bigger than 0. Okay, idea is very similar. We have to control the obliqueness, but it's a little bit more complicated than before, because if you look at the intersection point, this point has two normal directions. One is the normal of the free boundary, the red color. The other one is the normal of the fixed boundary, the black color. So you have two normal directions at the corner. And here you have one normal direction. So you have to prove obliqueness is holding simultaneously. So you have to control the angle less than pi over 2 for two angles simultaneously. Okay? So the last example I'm trying to talk about is a very interesting model. So, okay, it's a very typical example in optimal transport. So imagine initial domain is a round disk. It's a unit disk. And the target is two half disks. They separate from each other, okay? And Carfelli told us the solution can be written down explicitly. So the potential function is exactly given by half x squared plus x1 is this direction, okay? Plus absolute value of x1. So therefore, the gradient is identity mapping plus the sign of the variable x. The sign of x1. So what does that mean? That means if you use this gradient as an optimal mapping to map the disk, then the left part will be moved left forwards, okay, by 1 unit. And the right part is going to right by 1 unit. It will separate the target, okay? And in this example, you can see the solution, the potential function, is not smooth. It has singularity. The singularity is exactly the right segment here. Because along the right segment, this function is not differentiable. Okay, so that's a singularity. Now we're trying to understand if the domain is omega and the target is not half disk, it can be two arbitrary convex domain, omega 1, omega 2 star, okay? So for example, you have some kind of material in Sydney. You're trying to transport something to Brisbane, the other thing to Melbourne, okay? So question is, how can you divide? Which part goes to Brisbane? Which part goes to Melbourne? So in the hypersurface there, that's a singularity of the solution. Or you can think about it's a free boundary, okay? So it's a different kind of free boundary problem. So the question is, how can we study the regularity of such a free boundary? That's always our research. We're trying to understand the smoothness, okay? So that's a very recent work with Shibing Chen. So we prove as far as the target is separate and the bounded convex, and as far as the density function is bounded, we can prove the free boundary of the singular set is C1 alpha for some alpha between 0 and 1. If we assuming further the density function is C alpha, then we can prove the free boundary is C2 alpha. That's close question. That's the end of story. Once we have C2 alpha, we can go even further. So that means if everything is smooth, if the domain in Brisbane smooth, domain in Melbourne smooth, then we divide the material from Sydney smoothly. Okay, so everything will be smooth. Okay, so the difficult to study this problem is we do not have the interior ball. Let me go back a little bit to remind you what's an interior ball. That's an interior ball. It's very important in study the free boundary. But unfortunately, if you divide the domain into two parts, the interior ball is no longer be true. Okay, and how to handle this problem is again by uniqueness. So you have a point here. You have one point in Sydney on the free boundary. It's mapping to Brisbane, one target, Melbourne, the other target. Sydney has a normal direction, Brisbane has a normal direction, Melbourne has a normal direction. You have three normal directions. You have to control, again, the angle is strictly less than pi/2 simultaneously. But, however, this is in higher dimension. No one tells you these three normal direction is on the same plane. So you have to divide into many cases for discussion. It could be somehow, three vector, right? It can span into a R3 space. Okay, so it may not be exactly the same plane. So you have to control the angle very delicately. All right, I think a little bit fast, but we can finish here.